let us just get a glimpse of stars, okay? And today we'll ask ourselves initially the question as to what are different kinds of stars. Not in any great detail today. We will look at that in a bit more detail later. And what this picture shows you on the left is what is the Hyades open cluster. It is about 153 light years away from us. And the Hyades open cluster has been one of the fundamental sort of clusters which have been used for measuring distances and measuring the first rung or the first important rung in distance measurements of objects outside our own solar system or planetary system. And what you can see over here is that there are a number of stars, there are thousands of stars in this cluster, and it is part of the constellation Taurus. Taurus comes from the Latin word for bull, and you can see it over here that it forms the head of the bull over here. Now, this is a red giant star Aldebaran over here, which is about 65 light years away. There is another sort of cluster over here, NGC 1647, okay, the general catalog, 1800 light years away. And there is also a Pleiades cluster over here, which is 440 light years away. So a couple of things I would like you to notice over here. One is that these colors have been put as we would actually perceive it, all right? So Aldebaran is sort of yellowish, orangish kind of thing, yellowish color. And you can see that a lot of stars are bluish in color, okay? That is one aspect I would like you to note. And the second aspect I would like you to note is that, for example, I've said the Hyades open cluster is 153 light years. And some of these are members of the Hyades, okay, which are bright stars which you see. Whereas Aldebaran, a red giant star, is only 65 light years away, less than half the distance to the Hyades open cluster, okay? And when you see a constellation in the sky, whatever the constellation may be, whether it is Taurus, whether it is the Orion constellation or any of the other constellations, that what you observe are the stars projected onto the plane of the sky, all right? They could be at very different distances, but they made interesting patterns which enabled particularly ancient civilizations to easily identify them and also build myths and legends around them. So there were interesting sort of patterns which they wove interesting stories around. And that was, as we saw while talking about the history of astronomy, that was something which many cultures did. So when you see a constellation, the stars need not be associated, but they could be at very different distances from one another. It is only the pattern in the sky that one is talking about. Then in a given constellation or even in a given cluster of stars, that there could be stars of very different colors. So we'll try to understand what are the different colors of the stars maybe due to today. And we'll also mention that when I talk about clusters, in a cluster, the stars are all roughly at the same distance. They were probably born at a similar point of time, and they're all sort of under the gravitational influence to some degree with one another. The more outlying members, less so, but the inner members, more so. So I've used the term open cluster over here. So I'll spend a brief while just telling you the different kinds of star clusters, which one means in our galaxy as well as other galaxies, okay? See, the open clusters, I've shown you two pictures over here. The one on the left is an open cluster, and the one on the right is what is called a globular cluster. The open clusters are young stars, are young clusters. They're typically millions of years old, okay? And they're loosely gravitationally bound. They have irregular shapes. And as they move around, because we'll later see when we look at our galaxy, that the stars move around in a spiral galaxy, just as our sun also moves around the center of our galaxy, that they could disperse over time, particularly and the stars at the outer edges will disperse earlier than the ones which are more tightly bound, but they will disperse over time. They're largely found in the plane of our galaxy. Okay, our galaxy is like a disc shape with a bulge in the middle, but it has also sort of a nearly spherical halo. But these are found in largely in the plane of our galaxy. They occur in sites of recent star formation. And as I mentioned, they're young, relatively young, and one also uses the term that these are population one objects. Okay, this is just a jargon or terminology. That population one objects are young objects, and they're largely found in the disk of our galaxy. Now, if I were to look at globular clusters, you can see that visually also they look very different. You can see straight away over here that they consist of thousands of stars. Okay, and they could go up to about millions of stars. They're roughly spherical, they're gravitationally bound, and they're old systems. They're old clusters of stars. The ones in our galaxy are about 13 billion years old. So they perhaps formed right in the very early stages, and all the young stars would have evolved away rapidly, and they're found in the halo of our galaxy. They are metal poor, and I should mention over here that in astronomy, anything heavier than helium is referred to as metals, hydrogen and helium. Occur both above and below the plane. They form a spherical halo around our galaxy, and these are referred to as population 2 objects. Okay. Now, we'll look at this aspect a bit more detail when we look at the evolution of stars and stellar properties. But the young stars, which are more massive, live much shorter lifetimes than less massive stars, which live much longer. And these more massive stars are what you're seeing over here in these open clusters, and where these are largely old stars as well. Okay, so this is just a slight aside to introduce you to open and globular clusters. As we mentioned, the higher this cluster, which covers an important rung in our distance measurements, and we move on right now. To again reinforce what I said earlier. Sorry.
Sir, could you please explain what are population 2 stars?
Population 2 objects are objects which are generally old. They are metal poor, and they're not confined to the plane of our galaxy. They could be in the halo of the galaxy as well. Right? Whereas population 1 objects could be metal rich, and they're largely confined to the disk of the galaxy. Before addressing the question of whether the sun is a population 1 star, let me give you a brief overview of what are population 1 stars and what are population 2 stars. This classification was done by Walter Baade in 1944. Walter Baade was a German national, and during the war years, he was not allowed access to defense-related work, and he spent his time working, observing the sky with the Mount Wilson Observatory. And with the war being on, the skies were also relatively dark, and he made very detailed observations of nearby galaxies, and the Andromeda Nebula being one of them. And he noticed that the stars in the disk of the galaxy were different from those in the bulge or in the halo of the galaxy. The disk of the galaxy appeared more bluish, whitish, whereas the ones which were in the bulge or in the halo appeared more reddish or yellowish. And he coined these two terms, population 1 and population 2 stars. But he also recognized that these two types of stellar populations were recognized in our own galaxy by Jan Woerth way back in 1926, nearly 2 decades before Walter Baade's work. So the population 1 stars are basically metal rich. Metals are all elements heavier than hydrogen and helium. They are found primarily in the disks or spiral arms of galaxies. They orbit about the center of the galaxy, and they consist of both young and somewhat oldish stars. They could be millions to billions of years old. Metals constitute maybe at best about a few % of the mass of the galaxy. Young stars in Orion, as well as our sun, are examples of population 1 objects. This picture shows you Rigel and the reflection nebula IC 2118. Whereas metal poor are those which are poorer in metals by 110 to 100. It could be even parts less than that compared to the population 1 stars. So these population 2 stars are characterized being metal poor. They're found in the bulge, halo, as well as the disk of the galaxy. They have somewhat random elliptical orbits. They may move through the disk of the galaxy, but most of the time is spent outside the disk of the galaxy. For these ones which are, for example, in the halo. Their typical ages are of the order of 11 to 13 billion years. And they're believed to be old stars formed early in the evolution of the galaxy. Examples include globular clusters, halo stars, and one may ask oneself as to why does this difference arise? The difference arises because the more recent stars, the metal-rich stars, have formed more recently. As you know, stars are born in the molecular clouds, and those which have formed more recently, the interstellar medium, have been enriched by the remnants of the earlier generations of stars. Massive stars end their lives as supernovae, and the metals which are synthesized inside get thrown into the general interstellar medium of the galaxy. So future generations of stars keep getting made or are born from this enriched material or metal-enriched interstellar medium will be more metal-rich compared to the population 2 stars. The population 2 stars are believed to be old stars formed early in the evolution. So they're metal poor. They could be less than 1/10, less than 100, that of the sun, or even far less than that in some cases. They're found in the bulge, halo, and also in the disk of the galaxy. They could have random elliptical orbits, for example, those in the halo, as the slide in the middle shows. They could pass through the galaxy, go back, and although these halo stars or halo objects may pass through the disk of the galaxy, most of their time is spent outside the galactic plane. And since they were formed before the interstellar medium or the medium from which they formed was enriched with metals, they're metal poor. Examples include the globular clusters and the halo stars. Let me sort of reinforce what I said a little while earlier, that when you look at the constellation, which consists of objects of different distances, which appear sort of related because we see objects projected onto the plane of the sky. That here is, for example, the Orion Nebula. And don't worry about the magnitudes right now, because that is something which we'll introduce later, but just look at the distances, okay? You can find that they're all at very different, vastly different distances. The Orion Nebula, which is shown over here, is about 1350 light years away or so. But you can see that if we look at the different stars, which I've indicated over here, that they are at different distances. So this is just to reinforce the fact that when you see a constellation, the stars need not be physically associated at all. Okay, they are just projected onto the plane of the sky. Now we have introduced ourselves to clusters. We have introduced ourselves to population 1 and population 2 objects, and open clusters and globular clusters. And now we're going to have a brief look at what determines the colors of the stars. Okay, so can you sort of give suggestions as to what would determine the colors of stars?
Their temperatures and compositions.
Temperatures is the is one of the main contributors, because composition will play generally a smaller role. It can play a bit of a role in a very sort of low mass stars, which have because of a lot of molecular molecules which you will find in very low mass stars as well. But largely one of the main contributors is the temperature of the star. But why the temperature of the star and how?
Basically, if the temperature of star is a bit high, it would its black body radiation would peak in the blue range, and if it is a relatively cooler star, its black body radiation would peak in red region. Our
So,
star peaks somewhere in the yellow region, and since the color mix in a particular way, our star is a white color star.
okay, Daniel, thank you very much. What you're saying is absolutely correct. But I would just like you to think a little bit about one aspect of it, that when you actually, okay, we'll come back to that in a moment. Okay, so what determines, as you all have said, temperature is an important plays a vital role. And when you have a very hot star, it'll look more sort of bluish. And when you have low mass stars, low temperature stars, that you will get into the longer wavelengths, which is sort of towards the red end of the spectrum. Okay, and as you all have correctly said, that is determined by the black body temperature. All right, by Planck's radiation law, and you can go and estimate the temperature by applying the Wien's displacement law, where lambda peak, the wavelength at which it peaks, is multiplied by the temperature, is a constant. Okay. Now, for example, okay, now what I want you to think over, which I've given as an assignment later, but if you want to sort of give an answer right now, that's also fine. Now, for example, our sun, what is the surface temperature of it?
6,000 Kelvin.
Close to 6,000 Kelvin. Okay. Now, Daniel, you mentioned about the sun appearing sort of whitish, but if you look at this is the black body curve, which is about 5,000 degrees Kelvin. Okay, right? And this is about 6,000 degrees Kelvin, and our sun is a bit below that. Okay, so you can see that from this graph, it should really peak in the greenish region of the spectrum, right? Isn't it? Now, but we talk about red giant stars, we talk about blue stars, massive blue stars, but we don't never talk about a green star, right? Have you ever heard of somebody calling a green star?
Says because of how the colors mix in. When a star peaks in the green range, the other colors are also emitted, and because of the way they mix they mix with each other, that's why we perceive it to be whitish or yellowish in color. So there are no particular green or purple stars.
Exactly. Like when it's green, it'll also be emitting stuff on either side of it.
Yeah,
Not
excellent.
only and only green.
Yeah, both Ahan and Daniel, very good, excellent. So the thing is that you can see that the emission is emitted over a range of wavelengths, and what the way we perceive light is through the rods and cones which lie in our retina, right? And because of that, you'll find that that our eyes will actually combine the radiation, the red, green, blue, and will give you a roughly whitish or sort of whitish yellowish kind of color. So excellent, that's very good. Okay, now extending the black body spectrum to high energies, for example, we talked about the visible and the infrared, but you could also talk about objects which are extremely hot and could radiate at high energies, or some at lower energies as well. Okay, at the high energy end, for example, this we will again look at it in more detail later, but you'll find that neutron stars, which are the remnants of massive stars in its very early stages, which are born in the explosion of massive stars, could be extremely hot, several 100,000 to millions of degrees, billion degrees Kelvin or so, and they would be radiating at high energies. Okay, so this is something which is applicable beyond the optical region of the electromagnetic spectrum as well. Okay, now, I sort of wanted to show you this because this is an ideal thermal spectrum. Okay, an ideal thermal spectrum. That is what we have talked about in terms of a black body. But if you took an actual spectrum of a star, you would find absorption lines superposed on this ideal black body thermal spectrum. Okay, and the absorption lines arise due to absorption in the outer layer, cooler layers from the slightly inner photosphere, and this gives rise to the absorption lines in stars. So one of the characteristics of stars is an absorption line spectrum. There are also certain exotic kind of stars which from which you will see emission lines, but generally the stars are characterized by absorption lines along with its black body kind of spectrum. Okay, and these absorption lines give us very important diagnostics about the metallicities, about and trying to understand the physical conditions which are there on the surface of the star. Okay. Now, one thing I should mention over here that right now when we're talking of temperature, we are talking all the time about the surface temperature of the star. Because when you go to the interior of the star would be much hotter, and that is how nuclear reactions for generation of energy is possible. Now, can you think of any other aspect which could affect the color of a star? Temperature is an important aspect.
So,
yes?
I have a question. When we say the color of stars, we're saying the color of stars as observed from Earth, right? Like
color of a star, when we talk about, right now, when I say color of a star, I'm just referring to, in a very loose way, about what it appears to us. Okay. But later, what we will see is that we will define the color of a star in terms of its magnitude differences at two different wavelengths. Okay. For example, there would be in the U band and the B band. B band say is the blue band and V is the visual band, say. Okay. They would have different wavelengths. And I would denote the color of a star by the difference of the amount of light which is received at these two different wavelengths. So when I try to define it in terms of the amount of light, which we will see later when you define it in terms of magnitudes, we haven't come to the definition of magnitudes as yet, that right now take it as the amount of light which you receive, the difference at two different wavelengths, we will use that to denote the color of a star. Okay. For example, a hot star would be brighter in the blue region of the spectrum, whereas a cooler star would be brighter in the red region of the spectrum. So that would be a universal property. It need not be from Earth or from anywhere. Okay. So that would be an intrinsic property of the star actor. Okay.
yeah. Thank you.
Thanks for the question. Now, I was trying to get at what else can affect the color of a star?
Velocity and spin of the star.
Who said velocity and spin? Daniel, is it?
Yes.
Okay. No, so the thing is that the velocity is an interesting idea because when an object is coming towards you at very high speed, it will be blue shifted. When the object is going away from you, it will be red shifted, right? But the velocities of the stars are not so large. That it's a very small fraction of the velocity of light generally. But you will find instances in astronomy where plasma is moving or objects are moving at nearly the velocity of light. Okay, when things are moving at very high velocities, the frequency at which it is emitted and the frequency at which it's observed can be significantly different. And we know that galaxies, when we look at galaxies themselves and our structure of the universe, galaxies moving away from us, and the more further away they are, we talked about a Hubble-Lemaitre relationship while looking at the history of astronomy, that they're moving with higher and higher velocities, and there could be a substantial fraction of the velocity of light. So, in which case, for example, a line in the ultraviolet, for example, the Lyman alpha line, can shift to longer wavelengths, 1316 angstroms multiplied by 1 plus z, depending on the redshift. It can move whatever times, 1 plus z times, it will move to longer wavelengths. But when it comes to stars, the velocities usually are small. So your velocity is not going to play a very major role in terms of deciding the color of the star. And that goes for, pulsars are very rapidly rotating neutron stars. They can rotate as at the level of about millisecond. The whole class of pulsars called millisecond pulsars, which rotate once in about, I think the fastest probably 1.3 milliseconds, if I remember correctly, and so these can rotate very rapidly. All right. But the thing is that these are very complex objects, and these are not these are the end stages or the remnants of evolution of stars. And so I'm just talking about normal stars, like a sun, for example, or the stars in Orion, for example. So what is there anything else you can think about which may
So, any
composition of its corona?
Composition to some extent. Ekta was also saying something, or
So I was saying, if it passes through any gas clouds, maybe that could affect the color.
if it passes through any gas clouds, it could affect it. And that's you can draw the analogy from the sun itself, right? Because the sun, when you look up, it appears yellowish, but when you see through the atmosphere, it is more reddish at sunrise and sunset, isn't it?
Yes.
Okay. So the interstellar medium is also is the space between the stars. The light has to pass through that. And so if there is gas and dust, then it is going to affect the color of the star. All right. For example, even a hot sort of blue star with about very high temperature, 10,000 degrees Kelvin or more, when it passes through dense gas, it may look reddish. Here is for an example of a dust cloud called Barnard 68. Is one of these very dark clouds. And on the left, what you see is a composite image at 450 nanometers, 550 nanometers, and 800 nanometers. Okay. Now, this is largely, as you can see, in the visible region of the spectrum. So 450 nanometers will translate into 4,500 angstroms. All right. So this is largely in the visible region. And you can see in the center, you see nothing almost, right? Now here, it is taken the longer wavelength, 550, 800 composite, and it has gone to the infrared region of the spectrum, okay? 2200 nanometers. And when you go to the longer wavelengths, the longer wavelength light comes through. There is less of extinction at longer wavelengths. And you can see that the reddish color of some of these stars, which are seen at long wavelengths through this very dense dust cloud, okay? So these are two of the primary sort of reasons as to that one has to take account of while trying to understand the colors of stars. So that much for colors of stars. Now, what about colors of nebulae? For example, we talked about the Orion constellation, and we talked about the Orion Nebula, M42, is a region of gas and dust where thousands of stars are being born. And there's a bright glow at the upper left, which is M43. And there are very faint objects, brown dwarfs, at the bottom over here somewhere. Okay, okay. Brown dwarfs are quite stars which didn't quite make it. And what do you think determines the colors of these nebulae? Stars is something which we talked about, but let's spend a little time talking about nebulae. But before that, many of you probably know that how did the name Messier come about? Anybody, one of you? No? Okay. Charles Messier, a Frenchman, who was very interested in looking for comets. He was an avid comet hunter. And he made a list of diffuse objects in the sky so that he doesn't get confused when he's looking for new comets which he might spot. And he compiled a list of objects which are some of the most phenomenally beautiful objects, nebulae, galaxies, star clusters, which you can see in the night sky. Many of them are also visible to the naked eye. And so there are right now about 110 of these objects. But not all of them were actually put together by Messier when he first published it. Some of them were added to the list later by looking at Messier's notes. And so today the list is about, as far as I recall, it's 110 Messier objects. And each one has a number followed by, has M followed by a number. Okay, the Orion Nebula is Messier 42. Okay. And we'll see that Crab Nebula is one, which is the remnant of a star which exploded. And M31, our nearest galaxy, our nearest massive galaxy, which is very much like the spiral galaxy, like our own Milky Way, the Andromeda Nebula is M31. The Event Horizon Telescope, you may have read in the papers, which imaged the first black hole that was M87, a giant elliptical galaxy in the Virgo cluster of galaxies. So that is where the M name comes from. Now let's look at the colors of nebulae. Where does that come from?
So I'm guessing that the same reason quasar glows bright.
Quasar glows?
Like maybe it's the same reason why a quasar is bright in color, because of the friction of different molecules and gases.
Quasars. When you use quasar, what do you mean by a quasar?
A quasar is a black hole which is eating a star, and it's emitting X-ray, a lot of light and light energy in the form of X-rays, infrared and all.
Okay, we'll come to quasars in more detail later, but quasar is basically the nucleus of a massive galaxy, nucleus of a galaxy, which hosts a supermassive black hole, and it could be millions to billions of solar masses, the supermassive black hole, which accretes matter, and it emits across the electromagnetic spectrum, and its emission process is not the thermal process that we are talking about over here in stars, which is black body radiation, but it emits by non-thermal processes. And we will look at that in more detail. So quasars is not, quasars can heat up gas in its vicinity because of the ultraviolet radiation which it emits. But right now we are talking about stars. So quasars are the nuclei of massive galaxies. They belong to a category of highly active galaxies. Okay, so we'll hopefully get to quasars later, but right now we are focused on just stars.
Sir, another reason for the colors of nebulae could once again be like gases at different temperatures. So they have different absorption and emission spectra, and that leads to the colors.
Gas is it is gaseous. It has a temperature, and this Orion Nebula is a region of ionized hydrogen. Okay, and is referred to as an H2 region. It doesn't mean that there are no other elements. Hydrogen and helium are the two main sort of constituents. Hydrogen much more abundant than helium, but there will be traces of other elements as well. And it typically has a temperature of about 10,000 degrees Kelvin. Okay, so Ahan, Daniel, and Ekta have participated. I would like the rest of you to also sort of chip in. It doesn't have to be that you're right or wrong. It is just that I want you all to be engaged and thinking. All right.
My name is Akirno. Generally, in a lot of like this is probably other optical images, but a lot of the images you see that are very colorful, they combine images. What you see from different wavelengths of light. Like an optical telescope will see something different from a radio telescope. We'll see something different from the X-ray telescope. A lot of the times to get like pretty pictures, or just to get all that information into one picture, they'll color, let's say, the X-ray light blue, and the radio waves pink, and the optical light green, so you can just get all that information in one picture.
Akino, that is correct. Thank you, Akino. That you get that astronomers often combine images which are taken at very different wavelengths. For example, X-ray, optical, radio, because to get a complete picture of an astronomical object. Because the thing is that we cannot be spectral chauvinists, and to completely understand an object, you need observations at different wavelengths. Okay, but today we are actually concentrating on the optical region of the spectrum, optical and infrared and ultraviolet region of the spectrum. Okay, and you can see over here that this is an image of the Orion Nebula, which has been put together by using different filters within the optical largely the optical region of the spectrum. So here the X-ray has not come in, but Aquino, you're right that in many astronomical images, and obviously X-rays is not something which you can see, neither can we see radio, but they use false colors to try and bring out the different features at different wavelengths. Okay, But suppose we were looking at just the optical region of the spectrum. Suppose we're looking at Orion at just the optical region of the spectrum. Then what are the colors? How do the different colors arise? Okay, let's have a look at that. All right. Now, if you, for example, if you look at this image over here, which I just showed you, that it has used filters at different wavelengths. Okay. And because it is an ionized gas, what will happen is that it reaches an equilibrium temperature of about 10,000 degrees Kelvin. These regions of ionized hydrogen are referred to as H2 regions, okay? And H1 in astronomical literature refers to neutral atomic hydrogen, whereas H2 would be singly ionized hydrogen. Then obviously beyond that, we can't go in hydrogen, but you can see that when you go to heavier elements, for example, oxygen 3, doubly ionized oxygen, and so on and so forth. Okay, so so this gas, what is happening is being ionized by the ultraviolet or the high energy radiation from the hot stars which are forming. The Orion Nebula is part of a large molecular cloud, a cold, dense cloud of gas. It is from which stars are born. It is like a stellar nursery, and some of these massive stars will ionize the gas in its vicinity. Now, once the gas is ionized, it will also tend to recombine. So you will get from these nebulae, unlike in the case of the stars, what you will get are emission lines due to the recombinations. And once they recombine, they give off radiation as well. So with ionizations and recombinations, they reach an equilibrium, and the equilibrium temperature of these H2 regions is roughly about 10,000 degrees Kelvin. Okay. Now, what I indicated over here is that hydrogen alpha, which is H alpha, the N equal to 3 to 2 Balmer lines is at about 6563 angstroms. Oxygen 3 is more greenish, okay, roughly around 5,000 angstroms or so. Then there is also the broad blue continuum. Dust will scatter light, and also given the temperature, you will also get a continuum emission. So this is illustrating the same thing to you. This is an actual spectrum of an object, which I've given the references for all my slides below, so you should be able to look at them in greater detail when you like. And this is H alpha over here, okay? This is given in nanometers, okay? H alpha, which I just mentioned, 6563 angstroms, to H delta over here at 4,101 angstroms. So nanometers multiplied by 10 will give you angstroms. These are the recombination lines which you see. So these lines which actually you pick up will also affect the color of the diffuse nebulae that you see. And hydrogen being the most prominent one, that you'll often see a reddish glow in many of these ionized regions of hydrogen. Okay, and for example, suppose I want to just pick up these regions of ionized hydrogen, then I could make observations of the sky by having filters which just concentrate on this region of the spectrum. I will not look at any other light. I will just try to pick up, and because there could be some motion, I'll have to make it a little wider than just focusing on this, so that it allows for some kind of Doppler motion. And I do a survey of the sky, and then I will pick up the regions of ionized gas, okay, H alpha. So this is one aspect of what gives rise to the colors of the nebulae over here. So while you're still on nebulae, so we have talked about dark nebulae. We'll talk, which we saw can block off the stars, and some of it you may see at longer wavelengths, with stars appearing reddish because of extinction. You've seen the H2 regions where we saw the spectrum, the emission nebulae, but you could also, the universe is full of all kinds of other nebulae as well. Here is what is called a reflection nebulae, okay, near Rigel in Orion, and you can see it is bluish in color, all right? Why is it bluish in color?
Because it's reflecting bluish light from nearby stars.
Reflecting bluish light, but why isn't it reflecting reddish light? Is a region not very different from why the sky is blue, right? Because given these dust grains which scatter these light, blue would be scattered much more than the longer wavelengths, all right? And here is a planetary nebulae, I'm just giving you examples of other kinds of nebulae which are there in our galaxy. Planetary nebulae is when the outer layers of a star like our sun sheds its outer layers during the late stages of evolution before it settles down to its end state of being a white dwarf star. And this is the Crab Nebula, which is a supernova remnant. And here the process is thermal emission. But in a supernova remnant, there would be a mixture of both thermal and non-thermal emission. And this is the remnant of a star, of a massive star, which exploded. So we have been introduced today to at least not in detail, but different kinds of stars and different kinds of nebulae, and the two broad classes of clusters, star clusters, open clusters and globular clusters. Now, here is an image of an optical view of our galaxy, right? And we learned in the history of astronomy class that how the Aboriginal indigenous Australians had myths and legends around the dark spots in the sky, right? And these dark spots, as you will straight away jump at it and tell me right now, is because of absorption by clouds of dust and gas, which do not let the light from behind pass through, just as we saw for Barnard's Nebula. Now, what I want you to do, I'll give you a small sum here over here, that you can Google and find out the radius of the star, of our sun, and you can also find the distance to the nearest star, which is Proxima Centauri, is Alpha Centauri. And I want you to take out your pencil and pen and a little calculator, find out the distances, and calculate that what is the fraction of volume which is occupied by the sun in its neighborhood.
Sir, it's basically zero.
Never say basically zero. You have to give a number.
Just to clarify, when you say, so it's the volume of our sun divided by the sphere of radius, the distance between our sun and the nearest star?
That's right.
Okay. I've got an answer, teacher. It's the fraction is 5.2 times 10 to the power minus 24. I couldn't do it on a calculator, so I have to just type the numbers in Google. And if you want that as a percent, that's 5.2 times 10 to the power minus 22%.
Okay, we'll that's excellent. Okay.
An easy way to calculate it, so you don't have to worry about sphere stuff, because you're dividing a volume of a sphere by another volume of a sphere, is just to take the radius of the sun, divide it by the distance between the sun and the nearest star. And that gives you a ratio of distances. To get a ratio of volumes, you just cube it. So you don't have to worry about pi and 4/3 pi and such like that.
Okay, excellent, Aquino. Okay, now we'll look at that answer. Aquino is quite right. And the two other aspects I would like you to give me an input in a short while. We'll look at that answer is, what would an infrared image of our galaxy look like? And what would an ultraviolet image of our galaxy look like? Okay, what do you think it'll look like? And we'll try and explore this in a short while. And here I've just re-shown the image of our galaxy in the optical region of the spectrum, which shows the disk of our galaxy. This is in galactic coordinates, where the equator is the galactic equator, and right in the center is the galactic center. And what you see in the southern two bits over here, that's the large Magellanic Cloud and the small Magellanic Cloud, which are visible as diffuse patches of light in the southern hemisphere. Okay, and this is a mosaic of optical images covering the whole sky, which has been put together by Axel Mellinger. Okay, now let's look at what Aquino has calculated for us. And this is what I had sort of quickly put down. And it's about 5. Radius of the sun is this, distance Proxima Centauri is this, and you can get about 5 into 10 to the power of minus 24. Now you can see, what I want you to appreciate is that, suppose I were to just visualize what this number is, okay? That is, if I take 10 to the power of 8 millimeters that would be about 100 kilometers, right? Because 100 kilometers, you get it into meters by multiplying by 1,000, that's 5. Then you get it into centimeters, 100, that's 7, then millimeters, 8. Okay, so 10 to the power of 8 millimeters. So you cube it, that will give you a volume, right? That's 10 to the power of 24. So it is roughly like a small grain of sand till a distance, till a volume occupied by, I'm in Bombay right now, so it is sort of, as a crow flies, Bombay, Pune kind of distances that one is talking about. So what I want you to appreciate is that there is a very small fraction of volume which is occupied by the stars. You can see how tenuous our galaxy is, right? So it's a very small fraction, but the thing is that the interstellar medium, the space between these galaxies, is occupied by the interstellar medium of our galaxy, and most of the mass is in the stars, but most of the volume is in the gas and dust which lie between the stars, which is referred to as the interstellar medium of our galaxy. Okay. Now just your thoughts on what would happen if I look at the same galaxy in the infrared region of the spectrum.
So the dark spots that you see right now would have greater intensity in the infrared spectrum.
Sorry, say it again, Aman.
The dark clouds across the center, they would have a greater intensity in the infrared region, even though they do look dark right now.
You mean they would look darker or they would look brighter?
They'd look brighter.
They look brighter. Okay. Okay. And what about the ultraviolet? What do you think will happen in the ultraviolet?
Maybe the regions towards the fringes of the galaxy would look a bit like, I don't know how exactly it would change in UV actually.
Okay, let's see what happens. All right. Let's see what happens. This is an infrared view of our galaxy at different wavelengths. Okay. This is all sky maps of diffuse galactic emission at 12 microns dust emission. Okay. What happens is that this emission is due to dust, which gets heated up by the stars, reprocesses, and radiates at different wavelengths. And as Ahan correctly pointed out, that because the emission is long wavelength emission, you do not see the dark spots when you go to longer wavelengths. And we shall see later when we look at radio wavelengths, that is also true in the radio region of the spectrum. So here, what you see is largely dust emission. And these are at different wavelengths, but all in the different regions of the infrared region of the spectrum. And here again, you'll find that longer wavelengths will correspond to dust at lower temperatures. Okay? So these are maps put together from observations with different telescopes. And this is what I had mentioned a little while earlier about H alpha making a survey with a filter. And here you're not seeing the dark spot, but this is all foreground H alpha that you have picked up, which are basically foreground gas, which has been ionized by stars. And if you did an H alpha survey, these are the regions of ionized gas, which you're going to pick up. This has been done with the Wisconsin H alpha mapper, and it's called the Virginia Tech Spectral Line Survey, and the Southern H alpha Sky Survey Atlas, because this has combined data from both the northern and the southern hemisphere to look at the distributions of ionized gas in our own galaxy at both the southern and northern hemispheres. I was just showing you another example of a nebula illustrating the same aspect which we discussed earlier. Again, you can pick up this nebula. So you can see H alpha, nitrogen 2 on either side of it. Okay, and then there is oxygen 3, H beta, and as you go to dwarfs, you can see the higher H delta, H gamma, etc. Okay, so this is one good way of trying to pick out ionized gas. And Eta Carina is a remarkable nebula with even a more remarkable star inside it, which very brightened in around the 1840s, and now it is actually faded again. But I think it's again slowly rising in brightness. But it's quite a remarkable star right in the center of it. Now, just to illustrate to you what a galaxy might look like at ultraviolet wavelengths, I've tried to pick up the images of the Andromeda galaxy. Our galaxy is a bit more tricky to map because you're sitting inside it. But the Andromeda Galaxy is a galaxy which is very similar to our galaxy. This goes by the name again, M over here, M Messier 31. It's about 2.5 million light years away and 220,000 light years across. And the Milky Way and the Andromeda are among the two of the largest members of the local group of galaxies. We learn as we go along that galaxies also don't occur in isolation generally, but they are in groups and clusters of galaxies, and some are much richer than others. And we are a member of a group called a local group. Now, this is Andromeda in the optical region of the spectrum, and you can see it consists of, basically additions of emission from all the stars. This is the central region over here, and a lot of the old stars is what you see over here. Now, when you look at it in the infrared, what happens is that, as I mentioned, that it is the dust which gets heated up by the stars which are forming and re-radiates at infrared wavelengths. So in some sense, the infrared radiation is also tracing, if you choose it at the right wavelength, the star formation areas as well. There will be general cirrus, which is emitting infrared emission as well. But you'll find that some of these galaxies which are emitting very copiously in the infrared are starburst galaxies, where there is an intense burst of star formation and the gas is getting heated up and re-radiating at longer wavelengths, at infrared wavelengths. And these are referred to as ultraluminous infrared galaxies or hyperluminous infrared galaxies. But when you're looking at the ultraviolet, what you're picking up again from from the answers you gave about the color of stars, they are the high temperature stars. They are the massive stars. And so they would trace the regions where massive stars are being formed, and because massive stars usually last for not more than several million years. So these are the relatively recent sites of star formation. Our star, the sun, will last billions of years, but these massive stars live on time scales of millions of years. So an ultraviolet image picks up basically emission at shorter wavelengths. And you can see in this Andromeda Nebula, at least, that there is a reasonably close connection between where the dust is being heated up by the hot stars in the infrared emission, and in the ultraviolet emission, what you pick up are the stars themselves. Okay. So anything which is radiating at a high temperature, if it's at a black body, it will radiate at shorter wavelengths, and that is what you'll pick up. Massive stars, exotic stars, those are the kind of objects that you will pick up. Here is just another example. I pointed out the large Magellanic Clouds and the small Magellanic Clouds to you. These clouds were actually named after Magellan, who made the round the world voyage, and he carried a historian or the person who wrote up the account, Pigafetta, and wrote an account of these galaxies, and that's how the galaxies came to be known as the Magellanic Clouds. But the thing is that these were actually recorded earlier by Portuguese travelers as well, and of course the indigenous Australians, they would have seen them all the time. So here is an optical image of the galaxy, and these are irregular galaxies. Sometimes people call them barred spirals as well because of the prominent bar over here, but general nomenclature is that they're irregular galaxies. And when you look at these in the ultraviolet, you again pick up the hot stars. You can see this diffuse sort of light is much less prominent in this ultraviolet image. And this is the Tarantula Nebula, which is one of the most massive stars, over 200 solar masses or so, in the center of the star forming region, the Tarantula Nebula. Okay, these are, I'll post this. This is just for you to practice a little bit at home, just applying the Weyon's displacement law. And I've just given 2 stars. You can do it for more stars as you like. And the third question we already discussed in class, and you gave the answers. And the fourth one, I want you to just play around and see and find out how the Orion constellation look when you look at it from, say, Australia or Chile or South Africa, from the southern hemisphere. What would it look like? Okay.